All right, today we are continuing along with this topic of triangles. This unit 2 is a very, very short one, but it really kind of hits the ground running, gives us a lot of terms for the vocabulary with triangles and allows us to find some things. Yesterday, we talked about how all the angles inside of a triangle equal 180 degrees. We also said if you extended one of those sides out, that exterior angle equaled the sum of the two non-adjacent angles. So it gave us an opportunity to find some more angles, especially when all of a sudden you start to see this shape pop in. Before now, it was really just lines creating angles. Now we've got a shape in the mix. Well, this shape has some additional relationships that we're going to take a look at today. First one is a rather unique piece that can be added into all triangles, which is known as a triangle midsegment. So a midsegment of a triangle is a segment that's created by connecting the midpoints of two sides of the triangle. So in the diagram here, let me zoom in a little bit. An example of a midsegment that has been put into this triangle is segment DE. Now, some might ask, how do I know that that's a midsegment, or how do I know that it is connecting midpoints? Well, if I look at the diagram here, and maybe it'll help to put a clear, distinct point at D and E, I can confidently say that D is a midpoint on AB because AD and DB are congruent. They're equal halves. E is also a midpoint for the same reason. If you look at the little hash marks here, it is cut BC perfectly in half. So by definition, points D and E are midpoints, and simply by drawing a segment to connect them, wherever those midpoints may land, depending on the shape of the triangle, you create a midsegment. Now, the midsegment has some rules about it, some things that are true. It's all about rules in geometry. So if a segment joins the midpoints of two sides, aka if it's a midsegment, then the segment is parallel to the third side and half as long. So again, going back up to this diagram here, some things I could add to this image. First off, it's telling me that the midsegment DE is parallel to the third side where there was no midpoint given. So I could, if I wanted to, I could draw a little kind of arrow here on these two pieces to say that those two segments are parallel. Well, that opens up a whole new world of possibilities because we've talked about transversals with parallel lines, things like that. Consecutive angles, corresponding angles, all sorts of things. So that opens up a new world of possibilities, which will actually help us in the next unit as well. The second thing that it's also saying is that this segment DE is exactly half the length of AC. Now, again, the diagram may be a little deceiving. Maybe you're saying it looks a little too long to be half. That's fair. But mathematically, it is exactly half if you were to measure it. So again, kind of completing this little chunk of notes here at the top, using the diagram, I've added the features there. We would say that DE, segment DE, which is the midsegment, is parallel to segment AC, which when it refers to the third side, it's just referring to the side that did not contain the midpoint, creating the midsegment. Second thing we could say is that DE, there's two ways we could write this, that segment DE is equal to half the measure of AC. But if I wanted to think of that in reverse, I could also say that AC, which is the third side, is just double segment DE. So those are that's the same relationship, just described in two different perspectives. DE is half the length of AC. AC is double the length of DE. Now, again, with those relationships, you can start to find lots of calculations rather quickly. So mid-segments, that is what part of our notes are going to focus on here today. So taking a look here very quickly, these pictures get very busy. So that is usually the part that's a little hard for students, is that there's a lot of information going on here. But I'm going to take a look at this diagram and I'm going to try to clean up some of this information. I notice I have a triangle and it appears as though maybe 3 different mid-segments have been drawn in. Now, to confirm, those segments must be connecting midpoints on the side. So if I work my way around here, side QS, is it safe to say that W is the midpoint? Yeah, those little hash marks tell me that those are equal halves. What about side QR? Is X the midpoint there? Yeah, same reason, double hash marks. So those two sides, or those two halves, are equal. And then the same is true for side RS. Y is the midpoint there as well. So what we do in fact have are 3 mid-segments, each with respect to a different pairing of midpoints. Now, what it's asking us to do is identify pairs of parallel segments. And to do that, each mid-segment is parallel to the side for which it's not touching a midpoint. So I'll do the first one here. XY is connecting the midpoints of QR and RS. The side it's not touching is QS. So QY, the mid-segment QY, is parallel to the third side QS. So XY is parallel to QS. What's parallel then? I'll ask you for one. What's parallel to WX?
RS.
RS. And then I always lose track. What about WY? QR. Good. So lots of information going on in there. Throw in parallel lines, you start, again, you get to start to work your way through, start finding angles. It gives you opportunities to find additional information. Now, second one, again, same idea. In fact, almost identical. I'm going to run through this one a little bit quicker because, again, we have 3 mid-segments. Can be confirmed if you look, all the points have been cut in half thanks to those little hash marks. But what I have here is segment JK is parallel to side FH. KL is parallel to GF. And JL is parallel to GH. Again, if you have the 2 endpoints switched around on the same segment, it's still the same segment. It's just naming it in reverse order.
Could you not say KL is parallel to JF?
JL and JF.
So KL and JF, could you not just use that segment, or do you want to always use the whole line?
JL.
So K as in
and
kite.
L, I'm sorry. KL and JF. So yes, those would be parallel. That would be acceptable. Because if the whole thing is parallel, then half of it would still be parallel because they lie on the same line. Yeah,
Okay.
so that would be acceptable, absolutely.
Okay.
Which makes me realize that as I build a digital test, I will need to make sure that the answers it accepts take those into account as well. So thank you for keeping me on my toes, Chris.
No problem.
All right. So next up, working through now including measurements. So we talked about the parallel relationship between mid segments and the third side. Now let's take a look at values. So I'm going to do one of these. The other one's going to be pretty similar in terms of setup. So I'll give you the answers for the second one if you want to look for it. But this one here, it says if L, M, and N are midpoints. So it didn't give us the hash marks, but it did tell us, matter of fact, that these points here are midpoints. If you need to see those hash marks, you can work your way around the side there and add them in. That's up to you.
I got a quick question, Josh.
Sure.
So some of the hash marks are like 1 and then some of them are 2. Is that just like to verify like this is 1 midpoint, this is the second one, that's the third one, or?
It's to show a distinction between the pairings. So if it has a 1, these two are congruent to each other. 2s are congruent to each other, 3s. But what it also is telling me is that the 1 and the 2 are not congruent with each other. If they were, they'd all have the same number of hash marks on them. Yeah, so if you have 1 hash and a double hash, they are not congruent.
Thank you.
You're welcome. All right, so I added those in there. PR, let's see, this big side over here is 46. PQ, which is this side over here, is 40. And LN, ooh, they got sneaky on us. LN is a mid segment. It's 17. It is asking us to find 4 different missing measurements. So what I want to take a look at here, though, very quickly, is that LM is a mid segment, and so is MN is a mid segment. And then QR and MR, those are sneaky. QR is just a third side. MR, we're going to see, is just half of that same side. So once we find QR, we'll just cut it in half. Now, the relationship is that the mid segment is half as long as the side that it's parallel to. Or in other words, that side is twice as long as its mid segment, however you want to describe it. So starting at LM, LM is parallel to which side? LM
PR
is PR. So LM is parallel with PR, which means LM is half as long as PR. Well, I know how long PR is. What? Divided by 2. So I should get 23. Next one is MN. What is MN parallel to?
PQ.
Yep, good. So that means MN is half as long as PQ. PQ is 40 units. Divide by 2, we should get 20. The next one turns it upside down on us. We have mid-segment LN. We know it's 17. What is it parallel to?
QR.
QR. So LN is half as long as QR, which means what would I do with that 17?
Multiply it by 2.
Good. I don't want to go smaller. I already have the smaller of the two. So I'd multiply it by 2 to get 34. And then how'd I figure out MR?
Divided by 2.
Divide it by 2 again. So we're back to 17, but for a different reason. So there you have it. Next up, number 4, like I said, if you want to go through, jot down on the diagram, plug in the information you have, you're more than welcome to. I'm going to give you the answers to check if you want to go back and check later. But CE is going to be 14, DE should be 18, FH should be 12, and the last one's a little bit unique. It's asking you for the perimeter of the big triangle. That is just the distance around. So you would add those 3 side lengths together, which should give you a total of 56. So again, those will be on the video if you want them. If you jot them down now real quick, that's fine too. It's up to you if you want to go back and look at that one. I instead want to jump down to number 5 because here's a variable again. We want to bring back a little bit of algebra just to keep us fresh. And as I'm looking at this diagram, it's asking us to find X, and I notice I have what appears to be a midsegment, and I appear to have an expression for the parallel side as well. Now, how do I know for a fact that that is a midsegment?
It's cut in half.
How do you know those other 2 sides are cut in half?
This is the midpoint.
So I'm going to mark the points I think you're looking at. How do I know that these 2 points are midpoints? They are, but I'm just looking for what in that visual are you looking at that says, yep, it's in the middle.
The line.
The little hash marks, yeah. So these say that this one's cut in half. These little marks here say that one's cut in half. Connect 2 midpoints, you get a midsegment. That means that this midsegment right here is half as long as this one. Or in other words, this one is equal to 2 of the midsegments, right? Because it's 2 times as long. I'm gonna run with that. I'm gonna say that the 17x minus 18, which is the longer side, is just equal to double the midsegment. To double something, you of course multiply it by 2. And I get this relationship. I go into solving mode, multiplying it there on the right. I'm going to get 17x minus 18 equals 14x. Now, my algebra students, you're going to cringe because normally I'd say move the smaller of the 2, but I also know I'm going to it's all going to work out in the end. I'm actually going to move the 17x so I don't have a 0 on one side. It's going to save me a step later. So I get negative 18 equals, what is that? Brain fart, negative 3. Negative 3x, divide both sides by negative 3. I'm going to get x equals 6. Good.
Is number 6 set up about the same way?
Number 6 is dang near identical. So what I'm going to do on this one, instead of solving it all the way through, again, same visual cues. We have a midsegment here. If we double that midsegment, it has to equal that 3rd parallel side there. So that basically means if I took 2 times the 6x plus 31, that's going to have to equal the 19x minus 36. Now, if you take the time to solve that one, you should, and come up with x equals 14. If it doesn't, if you ever catch a mistake, please call me out on it. Don't just assume that I'm right. If you think that you've done something right and it doesn't match my answer, throw it out at me.
You did that one right. That one's right.
Oh, you already solved that one. Good.
Yeah.
Awesome. Thank you. So that's the power of a mid-segment. Mid-segment, again, is created by connecting two midpoints from two of the sides of the triangle. It creates a set of parallel lines, the mid-segment being half as long as that third side. So our next focus today, and this is actually going to run us through, in a manner of speaking, through the rest of our notes, is what's known as the triangle inequality theorem. And this is, if I were to boil it down and oversimplify it to you, this is basically the rule saying what three sides can form a triangle and which ones cannot. Because if you imagine for a moment, if you had three sticks, all of varying sizes, a lot of the times you could probably connect them to where each end of the sticks, when put together, would form a triangle. However, there are some lengths, albeit too long or too short, that no matter how you try to configure the ends of those sticks together, you can't actually form a triangle from them. Either you'll have extra going off the ends, or it won't be long enough to connect, to that third point. There's actually a way to figure out all possible lengths in that scenario, thanks to this triangle inequality theorem. So first, I'm going to give you the boring language, and then I'm going to show you what allows us to do. So the triangle inequality theorem states that a triangle exists if the sum of the two smaller sides is larger than the third side. So a triangle exists if the sum of the two smaller sides is larger than the third side. Obviously, the third side then meaning the longest side or largest side. So if you were given, like I said, three sticks, and if you knew their measurements, we can very quickly mathematically figure out whether or not it's actually possible to make a triangle out of them without even touching them. So we have 8 scenarios here. First idea or first recommendation for you is identify the two shorter sides. On number 1, what are they?
8 and 17.
8 and 17. Okay, so in order for this to be a triangle, the sum of those two shorter sides has to be greater than 24. What is 8 plus 17? 25. Is 25 greater than 24?
Yes.
Then yes. These 3 lengths would allow you to form a triangle. This is almost refreshingly easy, isn't it? Next one, number 2, what are the two shortest sides?
3 and 3.
3 and 3. So according to the theorem, the sum of those two sides has to be greater than the third side. What is 3 plus 3?
26.
6. And is 6 greater than 7?
No.
No. So if you had 3 sticks, 2 of them were 3 inches and the third one was 7 inches, no matter what you did, you wouldn't actually be able to form a triangle. Next one, jumble them up a little bit on you. What are the two shortest sides?
25 and 12.
25 and 12. So according to the theorem, the sum of those two sides, 25 plus 12, has to be greater than 35.
37.
So I get 37. Is 37 greater than 35?
Yes.
So yes. You guys get the hang of it? So if you want to continue solving those, that's fine. I'm going to tell you that the next one is yes, then no, then yes, then no, then yes. So again, same process. Find the two shorter ones, add them together. They need to be greater than the third. If they are, victory. You can make a triangle. If they are not, bummer. Can't do it. Now, that process is really handy if you already have three potential sides. You can test them out very quickly. What if I have two sides and I want to know all the possible lengths that I could use for the third side and still be able to make a triangle? Because it's not just one and only one answer. There's actually a variety for that situation. So we're going to see that out here on the next part. So this scenario is finding a third side given a range of possibilities. And we're going to let X in this situation, so we're going to use a variable, represent that potential third side. Now the trick to do this, I'm going to put it over here in the left-hand column. Our potential third side is going to be between two values, A and B. So it has to be greater than A. I know it's backwards. This throws you back to the nightmares of Algebra 1. When I made you learn compound inequalities, ew, gross. I said you never have to put them together. Well, here it just kind of happens. But X is between the low value A and the high value B. The way we find it, A is just the difference of two sides, and B is the sum of two sides. So if you look at the examples we're given here, we're given two sides. We need to find their sum and we need to find their difference. So we add them and we subtract them. So in the case of number 9, what is the difference of 14 and 22? Eight. And what is the sum of 14 and 22? 36. So what does that statement right there mean? What could my third side be? Well, it has to be greater than 8 or less than 30. Well, excuse me, greater than 8 and less than 36. So if you can think of any number that is between 8 and 36. Now, can I include 8? No, because that is not an equal to under that inequality. Same with 36. Can't use 36. But literally everything else between 8 and 36 is fair game. You could make a triangle from it, so long as the other two sides were in fact 14 and 22. So these next handful are kind of boring because you're just finding sums and differences. So on the next one there, the difference between 31 and 28 is 3, and their sum is 59. So that's even a wider spread there. Lots of possibilities. If your two sides are 3 and 11, the difference there is 8. And the sum is 14. So not a lot of opportunities there. a little bit more limiting. Next one is going to be between 26 and 64. The next one is going to be between 17 and 31. And the last one in this little section is going to be between 9 and 25. So again, let me bring that up on the screen there. It's just the difference of the two sides, the sum of the two sides. The third side can be anything in between. Now, if you look at these last two examples, it just takes it to the next level. It says if a triangle has lengths of 15 feet and 27 feet, check all possible lengths for the third side. Well, yes, there's a list there. We could sit there and test each of them individually, but I would go ahead, let's define the range first, and then just check all the ones that is in between. So the difference between 15 and 27 is 12. The sum of those two numbers is 42. So of the values listed, which ones are between 12 and 42?
34.
34, okay, 29
18.
and 18. What about 12?
No.
Right, because 12 equals 12. It's not greater than 12. Same for the next one. The range over there gives you two sides, 45 centimeters and 9 centimeters. They have a difference of 36 and a sum of 54. So within that range, which of the options there falls within that limit?
47.
Okay,
39.
47 and 39. Good. So with that being said, think about this. If I was into construction or woodworking or things like that, and I was trying to form a triangle, which if you've ever done any kind of building like that, triangles are one of the strongest shapes you can use to construct things. If you were trying to form a triangle and you know two sides, you can figure out very quickly what possible range of numbers you could use for that third side. So if you have a board that's too long or too short, you'll know straight away because you know all the possibilities within that range. Any questions so far? Okay. So next up is a neat little trick, a neat little relationship between the angles in a triangle with respect to the sides of the triangle. So we're going to start with ordering the angles. The angles of a triangle can be put in order by comparing the sides. There's a very direct relationship there. The smallest angle is always opposite the, any guesses?
Large.
The smallest angle is actually opposite the shortest side. Which then would mean that the largest angle is always opposite the longest side. So looking at the image to the left here, we're given all three lengths around that triangle. We are going to order the angles from the smallest to the largest. So what would be the smallest angle?
See?
Careful.
Sure. Yep. Sure.
Which is it? It's not. Which one's the shortest side?
A.
7 foot is the shortest side. Its opposite angle is A. So A is the smallest. What's the next biggest? Ask, what's the next longest side? The 10 foot, which is opposite angle C. Which then, process of elimination, angle B must be the largest angle. And I can say that without even knowing the actual measurements of those angles. Whatever they are in that order from smallest to largest. Now, the exact opposite can be said in reverse. The sides of a triangle can actually be put in order by comparing the angles. The shortest side is opposite the smallest angle. The longest side is always opposite the largest angle. So looking at the diagram here, now I'm missing a piece of information. I only have 2 of the 3 angles. Could I calculate the third one? How's that, Jonathan? You're right. They have to add up to be 180. So if I subtract the 103 and the 42, which is what, 145 total? If I subtract 145 from 180, what do I get for angle F?
35.
Should be 35. So that's helpful because now I know which one's the smallest angle. And the reason why that's important is because that angle F, the smallest one, is opposite the shortest side, which in this case is side DE. What's the next largest angle? E, it looks like, which is opposite of side DF, which then process of elimination, that leaves me with EF must be the longest side. So very important. If you think about it, it kind of makes sense though. If you had an angle opening up, if you imagine if I had string between the tips of my fingers here, here's a very narrow angle. As I increase the size of that angle, what happens to the distance between the tips of my finger? It increases, right? Increase the angle measurement, you increase that distance. Decrease the angle measurement, you decrease that distance, which kind of explains why there's such a direct relationship between an angle and the side opposite that angle. All right. So the next handful of examples here, oh, they're really sly. Watch out for the wording. I just caught this myself. The first 2 say order them from least to greatest. The second 2 say greatest to least. I think that was an unnecessary trick. Shame on the person who designed this. It wasn't me, actually, for once.
The last one say it too.
The last one's flip them around on you too? Okay. So if you wanted to take a moment, I'm going to do one. I'm going to do number 1 and then the rest. So long as you're careful, I think you guys could do as well. I'll give you the answers there. But taking a look at number 1, what is the smallest angle going to be?
17.
17 is the shortest side. So what is the angle opposite that side? M. So angle M is the smallest, followed by the probably what the 20 meters is the next shortest side. So angle P is opposite that, which leaves me with angle N. The next handful, again, I'm going to give you these answers so you can kind of check on your own. Number 2 should go angle T, then angle R, then angle S. Going in reverse order now. Greatest to least on number 3 should be angle C, followed by angle B, followed by angle D. And then the last one, angle X, then angle Y, then angle W. Yeah, we could sit here and do every single one, talk through every single one. I think you'd get really bored with that. Pretty repetitive. The next section, Misty pointed out, is kind of slide 2. It's doing the opposite. We're finding the sides here. Careful, it first wants it least to greatest and greatest to least. But notice they're a little bit sly here on this one because each of these 4 scenarios, they didn't give us the third angle. Don't just assume what it is. It may be worth calculating. And how would you figure out the third angle?
If you add 5731,
Add 5731, you get what? 88.
yeah, and then you subtract it from 180.
Subtract that from 180, and I think you get 92. Which is important now because that one is clearly the largest angle, which will affect how I answer this. So go ahead and see this one through. Starting from the shortest side, opposite the smallest angle, which is angle J. So the shortest side would be KL. Then the next smallest angle, or next largest, I guess, would be the 57, the L, which is opposite JK. And then that leaves JL as the last one. So again, I'm going to make the assumption that you can find the missing angles to confirm these next answers that I give you. So on the next one, in order from least to greatest, it would go ST, SV, and TV. And then the last 2, greatest to least, XZ would be the longest, I should say. YZ be the second, and then XY would be the last. And then example 8 would be BE, BD, and then DE. So again, to confirm some of those, you would want to make sure you went in, calculate that third angle, make sure you have all the information so you can order them from either least to greatest or greatest to least. All right, the last page is far more intimidating than what it initially seems because there's a whole lot of words there, but it has to do with the inequalities and then relating them to 2 different triangles to be able to make a comparison. So again, not doubting your ability to read, but I'll read it to you here for you real quick. The hinge theorem states that if 2 sides of a triangle are congruent to 2 sides of another triangle, normally we use little hash marks to confirm that, and the included angle of the first is larger than the included angle of the second, then the side opposite the angle of the first triangle is larger than the side opposite of the second triangle. What a mouthful. Here's what it basically says. Take a look at these 2 triangles. Can we confirm that they have 2 different congruent sides? Yeah. So normally we've been seeing them in the same shape, but this also now allows me to compare multiple shapes. So AB is congruent to ED, AC is congruent to DF. That is all I know about those triangles. However, thanks to this oddly named hinge theorem, I think it has to do with the hinge of a door and how it opens and closes. I don't know though. It says that if the measure of angle A, which is my triangle here on the left, is greater than the measure of angle D. Notice that A is the included angle between the pair of congruent sides, as is D. So if the measure of angle A is bigger than D, that must mean it's wider. So the opposite side, in this case BC, must also be greater. In this case, to EF. So basically, imagine if those two sides were my hands. No matter where I move my hands, they're going to be congruent length. Now over here, try to put it in the frame of my zoom as well. Over here, if my angle is narrow, the distance between my fingertips is rather short. But then I move over here and make my hands wider. My hands are still my hands, same length. But what has happened to the distance between? It's got bigger. This triangle is shorter. This one is bigger. This angle is smaller. This angle is bigger. It's basically the same relationship as what we're just doing with the other inequalities, but now it's saying that it's enough so long as you have two congruent sides. I should actually probably go highlight that one real quick. Two sides of a triangle are congruent to two sides of another triangle. That is important. You can't just take two random triangles with just all various sides. You have to have two congruent. Then this works. Now, the converse of that theorem, also really wordy. I don't know why it has to be so wordy. Basically says the exact opposite. So in this case here, if you know that the side length opposite the included angle, so in this case BC, is greater than side EF, that is enough to say that the opposite angles are that same relationship. The measure of angle A must then be greater than the measure of angle D. So, really wordy way of saying you make the angle bigger, you make the other side bigger, regardless of whether it's in the same triangle or two different triangles with congruent pairs of sides. So, last handful here, we're doing better for time than I thought, which is nice. That means we got a little time to work today, and Monday as our catch-up day will be nice as well. We have some situations here. Some of them are very point blank. We can make that comparison pretty quickly. Others, we're going to have to do a little finagling, make a computation or two to be able to definitively give our answer. So starting with number one. First off, in order for this hinge theorem to work, we have to have two congruent sides. Do we have that? Ooh, careful. This one snuck up on you. It gave you numbers instead of little hash marks.
Yes.
So if you look over here, JL and NM are congruent, and then JK and NP are congruent. If you need to add those hash marks, please do so. Hopefully by now your eyes are starting to attune to seeing those anyways. So that means then we're focused on the included angles. Okay. So which one's bigger? 79 degrees, which is opposite which side? KL. So KL is going to be bigger than PM. Yeah. So KL is greater than PM. This next one's rather sly. You're going to see this kind of diagram come up more often in the next couple units. It's kind of mean because what it's about to do is deceive you. Do you see two congruent sides?
No.
gonna say yeah, but you know it's no. Well, actually, you should have stuck with your first answer because it is actually yes.
Because of the 24.
Well, I'll show you. So the 24s, can we agree that AB is congruent to DC?
Yes.
Well, if you look at these two triangles, they're actually sharing a side. Doesn't BD equal BD?
Yes.
Yeah, or BD equals DB, depending on how you look at it. So this one was sly. It was in there because it was the same one. So that happens a lot. That's going to come back again. So kind of maybe make a mental note of that. But the two included angles then we're looking at is the 59 degrees and the 65 degrees. Which one's larger?
65.
65, which is opposite which side length?
AB.
Ooh, careful. 65, we're in this triangle over here. It's going to be opposite BC. So BC must then be greater than
AB.
AD. Now, that actually means we use a less than symbol because of the order that they gave them to. If you recall, way back in elementary school, when they taught me this, they said, think of the inequality sign like an alligator. The alligator's very hungry. His mouth is going to go towards the bigger one. It's cheesy, but it worked. So yes, BC is greater. So we don't want to use a greater than symbol though, because it's on the other side. Next one, similar situation, kind of sly here. Let's first find those congruent sets of sides here. I see one that's labeled the 3s. And this one again is one of those sly ones. They're sharing a side. Now, here's the catch. I have the included angle for WXZ's triangle. I don't know this included angle right here, because this is the angle that's between those two congruent sides. Do I have enough information, however, to calculate it?
Yes.
I hope so, because if you look inside this triangle, I know the other two angles. So 93 and 32 add up to 125. What does that leave me for the 180 that should be in there?
55?
55. So, gosh, I don't know how to squeeze it. I'm going to do this. So this 55 is the other included angle we're looking at. Which one's larger?
93.
Oh, careful. That's not one of the included angles. It helped me find the one I was looking for, but I don't need it anymore.
55.
The 55 and the 55, if I kind of land there where that angle is formed in the corner and follow it to the opposite side,
That's why.
XY is greater than the WX. But this one they have backwards as well. So I'm going to actually use a less than symbol. So if XY is greater, that must mean WX is less than XY. All right. This gets pretty repetitive all the way through. I'm going to give you number 4s because it's just more of the same. PQ is going to be greater than PS. I want to show you real quick though, at least 2 of these other ones because it's using the converse of the hinge theorem. So instead of comparing the sides, it's comparing the angles. But remember, the same idea still works. You still want to find the congruent pair of sides though. Spot those first. So I'm looking at this one. I see 25 and 25. So ED and HI are congruent. And then I see the 16. So DF and GH are congruent, which means the side not in that comparison is the 33 and the 35, which is opposite the included angle. Which one's bigger?
35.
35 is longer, so which angle is larger? D. Number 6, again, focus in on those congruent pairs of sides. I see the 12 and the 18s, which means the sides that I did not include was the 15 and the 16. The 16 is opposite of angle A, the 15 is opposite of angle E. Which one's bigger? 16, which is opposite angle A. So angle A is greater. Now, for the sake of your eyes, I'm going to highlight the sides that are not congruent for the last two, but I will leave you with calculating those yourself. I will give you the answers though. Angle RSQ is less than angle TQS, and angle JMK is less than angle LMK. That, ladies and gentlemen, is that.